Imagine perfectly cloning a massive 100-story digital skyscraper. You do it in milliseconds.
Yeah.
But then your entire operating system just completely crashes because you tried to copy the front door.
Right. It's such a wild concept, but it happens all the time.
It really does. So today we are doing a deep dive into the exact moment that software hits a brick wall. Like that invisible boundary between a programming language's internal memory and, well, physical reality.
And it is a hard boundary.
Exactly. We are pulling from this really fascinating technical piece by Aaron Rose. It's titled The Secret Life of Python, Why You Can't Clone the Physical World. And what makes this source so cool is the format.
Yeah, it's not your standard documentation.
No, not at all. Instead of a dry, textbook page, Aaron actually frames this whole deep dive as a narrative that's set in this grand, quiet Victorian library in London. And in this setting, code craftsmanship isn't just like a best practice, it's the entire culture.
Framing it as a story is honestly a brilliant way to illustrate these complex architectural boundaries. Because, when you strip away all the syntax, code is fundamentally just a managed environment, right?
Right.
It operates in this highly controlled, isolated little universe. But inevitably, it has to reach out and negotiate with the very messy external operating system that's actually governing the physical machine.
And that negotiation is where things go wrong.
Oh, absolutely. That is where most developers run into trouble.
Yeah, so if you are listening to this right now and you've ever built, say, a web scraper or an automated script, maybe a database tool, you have probably slammed into this exact boundary without even realizing what was happening under the hood.
You almost certainly have.
So let's step right into that library. Sitting at one of these big, heavy oak tables is Timothy. He's a junior software engineer.
Oh, the classic junior engineer phase.
Yes. Timothy is currently experiencing that euphoric phase of coding where he feels totally invincible. He has mastered the art of cloning pure Python objects.
Right, he's just bending data to his will.
Exactly. He is comfortably manipulating massive, deeply nested dictionaries and lists, basically living in this purely internal world where he makes all the rules.
Every developer goes through that honeymoon phase, honestly. Working entirely within the language's own internal memory heap, it feels frictionless.
Because it is, right, for the most part.
Mostly, yeah. You allocate memory, you ask for a copy of a massive data structure, and the interpreter just handles all the recursive traversal. It gives you a perfect duplicate instantly, but it creates this totally false sense of omnipotence.
And Timothy's about to push that omnipotent a bit too far. So he is building a chess club application.
Okay.
And he needs it to persist data to the real world. So he writes a class called a match logger. Its sole responsibility is to record every single move of a chess match into a physical text file that's just sitting on his laptop's solid-state drive.
And right there, that is the critical transition point in his design.
Because he's leaving memory.
Exactly. He is moving from abstract data structures floating in volatile RAM to requesting a tangible, persistent resource on a physical disk.
Right. And here's where it gets tricky. He wants to add this feature to let players explore alternate what-if scenarios.
Oh, like branching time.
Yes. So a player might wonder, what if I had moved my knight instead of my bishop on turn 12?
Okay.
To accommodate this, Timothy needs to branch the game state.
Makes sense.
But to keep the game logs totally separate for these alternate timelines, he tries to do what has always worked for him in the past. He takes his match logger instance and he uses Python's deep copy function to just clone it.
He just tries to duplicate the whole thing.
He hits run, totally expecting a seamless parallel universe to spin up. But instead, the console just spits out this bright red wall of text. It says, type error, cannot pickle I.O., text I.O. wrapper object.
Ouch!
Yeah, the execution just halts completely.
And that is the exact moment the illusion of omnipotence shatters. Python explicitly refuses to duplicate the logger.
Okay, I have to put myself in Timothy's shoes here, though, and push back on the interpreter's logic. Because if I am writing code on a machine with, 32 gigabytes of RAM, and Python can effortlessly duplicate a 2 gigabyte pandas data frame in a fraction of a second.
Which it can, yeah.
Right? Why does a tiny pointer to a 1 kilobyte text file break the entire system? Pickling is just serialization, right? Converting an object into a byte stream. So why can't Python just serialize a file object?
It's a great question. To understand the interpreter's refusal, we really have to look at what serialization actually does. Or, more importantly, what it assumes.
Okay, what does it assume?
When Python pickles an object, it's translating the object's internal state, like its variables, its data, into a format that can be reconstructed later. Python can serialize its own memory constructs because it owns them.
Right. It made them.
Exactly. It allocated the bytes for that data frame. But a file object, like that text.io wrapper Timothy hit, is not just data. It is a representation of an active, live connection to an external reality. And Python does not control that reality.
And this perfectly introduces Margaret. She's a senior software engineer in our Victorian library story. She pulls up a chair next to Timothy to explain the mechanics of this wall he just hit.
She's about to drop some wisdom.
She is. She introduces the concept of the boundary and the landlord. Margaret explains that a file on a hard drive is a physical resource, and it is guarded fiercely by the operating system.
Because the operating system, whether you're on Linux, Windows, Mac OS, whatever it is, the absolute authority over the hardware, Python is really merely a user space application running under the landlord's roof.
Just a guest in the house?
A guest, exactly. When Python wants to read or write to a disk, it cannot just reach out and touch the physical platters or the flash memory blocks. It has to make a system call to the OS kernel. It has to politely ask for permission to access that specific file path.
And Margaret uses this analogy that I think just perfectly clarifies this restriction. She tells Timothy to think of a file like a rare book in this grand library.
I love this analogy.
It's so good.
Yeah.
She says, if you need the information inside the book, you can take it to a copy machine and photocopy the pages. The pages represent the data. You can copy those all day long.
Right. Deep copying the data frame.
Yes. But you cannot photocopy your permission to borrow the book.
No, you can't.
You can't take the librarian's official checkout stamp, duplicate it on a piece of paper, and hand it to your friend so they can walk out with a second copy of a book that doesn't even exist.
And the mechanics underneath that analogy are just fascinating, because when the OS grants Python permission to open a file, it issues something called a file descriptor.
Okay, what does that actually look like?
Well, in systems like Linux or Mac OS, a file descriptor is literally just an integer, like the number 3 or 4.
Wait, really? It's just a single number?
Just a number. That integer is an index pointing to a highly protected table inside the kernel's memory space. That table tracks which processes have access to which physical files, where the read/write cursor currently is, and what access rights are granted.
Oh, wow. So Python is literally just holding on to the number 3.
Yes. So if deep copy were to blindly serialize and duplicate the Python object, it would just be duplicating the integer 3.
It's not actually copying the connection.
Not at all. It wouldn't be telling the kernel to open a new connection or allocate a new entry in those protected tables.
But wait, if Python is so powerful, why can't it just forge that OS permission slip? Like, what actually happens if it bypasses the pickling restriction, copies the integer 3, and just hands it to the cloned match logger? Why is the OS acting like such a jealous bouncer over a simple text document?
So that leads directly to what Margaret calls the double booking disaster.
The double booking disaster.
Let's play it out. Let's say Python forces the clone. Now you have 2 completely separate match logger objects running in your code. Because they were forcefully duplicated, they both hold the exact same file descriptor integer. They both genuinely believe they have exclusive write access to the exact same physical file on the hard drive.
Oh, no.
And they both think they control the cursor position.
So if we imagine the 2 chess games proceeding simultaneously, Game A, the original timeline, is playing out. Game B, the what-if timeline, is also playing out. They both think they own chesslog.txt.
Right.
Game A's logger tries to write knight to e4. But at that exact same millisecond, Game B's logger tries to write queen to h5. What happens?
Because they share that underlying kernel pointer, they do not queue up politely. The write buffers just flush to the disk simultaneously.
They just crash into each other.
Exactly. The bytes interleave. You wouldn't get a clean log of Game A followed by Game B. You would get literal file corruption. The text file would read something like king, queen, knight to h4-5.
That's completely unreadable.
The data is destroyed.
Okay, I still want to challenge this from an architectural standpoint, though, because hardware is incredibly fast today. Why couldn't Python just cache all of Game B's file operations in a separate block of RAM, let Game A finish its thing, and then write Game B's cache to the disk sequentially later? Why crash the program immediately?
It sounds plausible, but caching in RAM introduces a fatal vulnerability regarding state synchronization.
How so?
If you cache gigabytes of file operations in volatile memory, and the power cuts out or the application crashes for some totally unrelated reason, all that saved data just vanishes. because it was never actually committed to the non-volatile disk.
Right, it was just hovering in RAM.
Exactly. The OS enforces strict file handles because it absolutely must guarantee that when a program is told a byte is written to the disk, that byte is physically magnetized or stored in a flash cell.
Oh, I see.
So by throwing that type error and crashing the program the exact moment Timothy tries to clone a live file handle, the OS is actually acting as a guardian of data integrity. It prevents a scenario where the application state diverges irreparably from the hardware state.
So the error message isn't a punishment at all. It is a structural safeguard.
Exactly.
But, understanding that doesn't actually solve Timothy's immediate problem. He still needs to branch his chess logs for the players. We have firmly established that he cannot clone the live connection. The direct brute force approach is blocked.
Right, so he has to shift his entire conceptual framework here. Instead of trying to clone the live object, he needs to clone the configuration required to build a new object.
And Margaret phrases this beautifully in the source material. She says, you don't clone the handle, you clone the intent.
Cloning the intent. It's a profound shift in mindset.
It sounds like a great philosophy, but what does that actually look like in the code base, like practically?
Yeah.
Well, the author, Aaron Rose, actually includes a specialist tip cheat sheet breaking down the exact mechanics.
Yeah, that part is super practical.
Timothy basically has to intervene in the duplication process by writing a custom deep copy method inside his matchlogger class.
Because the standard implementation of deep copy just recursively traverses an object graph. It uses a tracking dictionary called a memo to avoid infinite loops if objects reference each other.
Right.
But when you define a custom deep copy method, you are intercepting that automated traversal. You tell Python, stop guessing how to copy this object. I am going to manually construct the clone.
And the cheat sheet outlines the exact steps. First, Timothy's custom method creates a brand new, totally empty instance of the matchlogger class. And it explicitly bypasses the standard initialization sequence so it doesn't immediately try to open a file.
Which is key.
Right. Then, it copies over the internal data variables from the original object's dict attribute.
Right. The dict attribute is where Python stores the dynamic state of an object. But here is the critical intervention. Timothy intentionally strips out the text.io wrapper object, that live file handle, from that copied state.
So he just leaves it behind.
He ensures the clone does not inherit that integer pointing to the kernel's file table.
Instead, he passes the string of the file path. He manipulates the string to create a new file name, maybe appending, underscore alternate timeline to it. And then he commands the cloned instance to call its own open method.
Yes, and by doing this, he forces the clone object to walk up to the OS kernel, present a brand new file name, and negotiate its own fresh file descriptor.
The clone acquires its own legal permission slip from the landlord.
Exactly. You are teaching the descendant object how to start fresh and legally acquire its own resources, rather than forcing an illegal duplication of a physical asset.
It's basically like realizing you cannot use a photocopier to duplicate your friend's rental car.
Oh, that's a good way to put it.
Right. Like instead of trying to forge the keys and the engine and the license plate, you just write down the address of the rental agency, hand it to your friend, and tell them to go sign their own lease for a new car.
A perfect architectural parallel. You are replicating the parameters needed to achieve the state rather than duplicating the live state itself.
But, giving your code the autonomy to negotiate its own leases with the OS, that introduces a massive new responsibility.
It really does.
Once Timothy's objects have the power to independently open separate file handles for every alternate timeline a user explores, those resources are going to accumulate.
Fast. Leaving a file handle open indefinitely is a slow, silent killer of applications. It's known as a resource leak.
Because the OS doesn't have unlimited resources.
Exactly. The operating system only has a finite pool of file descriptors available to hand out. If Timothy's code keeps requesting new permissions to borrow from the library but never actually returns the books, eventually the OS will simply refuse to grant any more.
And what happens then?
The application will just crash with the too many open files error.
And this brings us to Margaret's ultimate whiteboard lesson in the library. She writes down the Guardian Rule.
The Guardian Rule.
She tells Timothy that whenever an object touches the outside world, whether it's a file, a network socket, or a database connection, it must adhere to this rule. Never assume a resource will close itself, and never try to clone a live connection.
And implementing that guardian rule requires stepping away from manual management. You have to utilize structural guarantees.
How do we do that in Python?
In Python, this is achieved through context managers, relying on two specific built-in methods, the enter method and the exit method.
And when you define these methods in a class, you change how it behaves when it's paired with a statement in Python. Margaret frames this so brilliantly. She says that implementing the enter and exit methods turns your object into a safe room for the external resource it manages.
I love the safe room concept. Let's examine the mechanics of that. When the execution flow hits the with statement, the enter method fires.
Okay.
This is where the object officially requests the resource from the OS, secures the file handle, and brings it inside the isolated scope. The code block then performs its read or write operations.
Right. But the real magic happens when the code finishes. Or, actually, more importantly, when something goes terribly wrong.
Yes, the disaster scenario. If the program encounters an unexpected error, say a network timeout or a random division by 0 while that file is open, a normal script would just crash immediately, right?
Leaving the file handle open.
Exactly. Leaving the file descriptor locked and orphaned in the kernel's tables. But a context manager intercepts that failure.
Because the exit method is structurally guaranteed to execute, no matter what happens inside the safe room.
It acts as a mandatory cleanup sequence. The exit method captures the exception type, the value, and the traceback, which allows you to log the error if you need to. But its primary job is to execute the close command.
Returning the integer.
Yes, returning the file descriptor integer to the operating system's available pool before allowing the program to crash or continue. It guarantees the lease is terminated properly.
Looking at Timothy's journey through this whole deep dive, it completely changes the definition of what makes a good developer, I think.
It really does.
Like mastering the internal logic, sorting the lists, querying the dictionaries, that is just table stakes. True craftsmanship, like the actual leap from being a scripter to being an architect, happens when you learn how to manage the life cycles of external realities.
You are shifting from merely processing data to managing the temporary leases your software takes out on the physical hardware. Recognizing that boundary between internal memory management and external state synchronization, I mean, it's just fundamental to building resilient systems.
Definitely. And if you are listening to this, the next time you write a script that opens a file or queries a database or even just pings an external API, look at how you are managing that boundary. Are you haphazardly passing live connections around your code base, just hoping the garbage collector cleans up the mess? Or are you cloning intent and building safe rooms for your resources?
It's a vital question to ask.
Understanding this distinction just gives you a much deeper appreciation for the silent guardrails, keeping our digital infrastructure from collapsing under its own weight.
Because without those rigid boundaries enforcing intent and lifecycle management, concurrent computing on modern operating systems would just be impossible. It would be chaos.
Total chaos.
Yeah.
And as we wrap up this analysis, let's take the architectural philosophy we just explored and push it one step further.
Okay.
We've spent this entire deep dive looking at how hardware enforces strict rules.
Yeah.
We've seen that if an operating system enforces unbreakable guardian rules and will literally crash your application to prevent you from mishandling a simple kilobyte text file, consider how those same architectural principles apply when the external resource isn't a file, but an API token granting access to a live user's private data.
Wow, yeah. Or like an OAuth session managing permissions across microservices.
Exactly. If your code is expected to be this rigorous about securing a lease just to write a chess log to a disk, ask yourself, how structurally sound are the safe rooms in your architecture when you are managing the life cycle of external human data?
That is a heavy thought.
Are you carefully passing the configuration and cloning the intent? Or are you illegally duplicating permissions you don't actually own? It is a technical parallel that demands the exact same level of craftsmanship.